Hello everyone, myself Sanjay along with Pradeep and Satyam are going to present AVL Trees, which is an example of balanced binary search tree. So today we will discuss about AVL trees and some of its properties. After that we will look into the code of AVL trees and we will conclude by discussing some of the applications. So here is the contributions by each of our team members. While introducing a new data structure, the first thing that comes into our mind is why do we need one more data structure like this? For binary search tree, for there was a problem. So in order to solve that, we introduced the concept of balanced binary search tree. The structure of binary search tree depends on its insertion order. When a BST when the elements are inserted in ascending or descending order, the BST will be a linked list like structure. So in this situation, we have to traverse a linear time to do search, insert, or delete operations. This increased complexity is a problem for us. In order to solve that, we have introduced the concept of balanced binary search tree. So in balanced binary search tree, the complexity of insertion, deletion, and searching will be log n. So what is a balanced binary search tree? The height difference between left and right subtrees are maintained to be a minimum amount in order to do complete operations like insertion, deletion, and search. In 1962, we introduced the concept of AVL trees, which is an example of balanced binary search tree. The fact about AVL trees is that the difference between height of its subtrees will be at most 1. That means it can be 0, 1, or minus 1. There are mainly two properties of AVL trees. The first one is balance factor and the second one is rotation. So what is balance factor? It is the difference between height of left subtree and height of right subtree. For AVL trees, it will be 0, 1, or minus 1. Now we can calculate the balance factor of a BST. Here you can look at the node. The left subtree has height of 2 and the right subtree has a height of 2. So it will make the height difference or the balance factor 0. Now take this node where 29 is the value. It has the left node as height 0 and there is no right subtree. It will make the balance factor as 1. Here this node 82 has right subtree has 0 height and the left subtree has 1 height. So it will make 1 minus 0, that is 1. Now I will hand over to Satyam to introduce the concept of rotation.
Now let us understand the rotation in AVL trees. There are 4 different types of rotation in AVL trees. First is single rotation. In single rotation we have 2 different types of rotation. One is left rotation, which is LL imbalance. Another is right rotation, which is RR imbalance. And the other type is double rotation. In double rotation we have two different types. One is left right rotation, which is LR imbalance. Another is right left rotation, which is RL imbalance. Now let us understand one by one. Let's understand left rotation with the example here. Now we can see that we have a left skewed binary search tree with 10, 9 and 8. Now we can see, we can calculate the balance factor for all these elements. Here the balance factor of all these elements are given, and we can see the balance factor of this node is 2. But in order to make it a balanced tree, the balance factor of all the nodes should be either 0, 1 or -1. So this node is making this tree as imbalanced. So we need to make a rotation in such a way that the balance factor of all the node becomes either 0, 1 or -1. So here we can make a clockwise rotation from this edge, which makes it in this form. Now the balance factor of all these nodes are 0. So now this tree is balanced tree. Now let us understand right rotation, RR imbalance. In this example, we can see that here we have a right skewed binary search tree, and now we can calculate the balance factor of all these nodes, and we can see the balance factor of uh, this particular node make it imbalanced because the balance factor of this node is not 0, 1 or -1, it's -2. So we need to make a rotation in such a way that the balance factor of all the node become either 0, 1 or -1. So we can make a rotation in anti-clockwise direction with through this node edge, and we will get the structure in this format. Now the balance factor of all these nodes are 0, which make it a balanced tree. Now another type is left right rotation, which is LR imbalance. Now in this example we can see that we are calling it is LR because the first uh, imbalance is L and the another edge through the another edge is R. Now we can convert it to LL imbalance by making a anti-clockwise rotation through this edge. And here after making a rotation we can calculate the balance factor of all these elements, and now the balance factor of these are 0, 1 and 2. This node is making it imbalance. So we need to make a rotation in such a way that the balance factor of this node also becomes either 0, 1 or -1. So we have already studied how to convert LL imbalance tree in a balanced tree. We can make a clockwise rotation, and after that we get such a structure. Here the balance factor of all these nodes are 0. So it's a balanced tree. Now let us understand right left rotation RL imbalance, which is the last one. Here we can see that this LR imbalance tree, here the balance factor of all these nodes are 0, 1 and -1, -2. So we need to make a rotation in such a way that the balance factor of this node becomes either 0 or -1. We can make a uh, anti-clockwise rotation through this edge, and now it's become a structure with having balance factor 0 in all these nodes. Now it's a balance tree. Now we have already learned all the four rotations. So here's the example of insertion and rebalancing. The question is, how many rotations are required during construction of a AVL tree if the following elements are added in the order given? So when these 35, 50, 40 and 25, these are the elements and these are the options. Now let's understand. So when we add 35, we don't need to calculate the balance factor. When we add 50, we don't need to calculate the balance factor because the balance factor will be at this moment it will be at most 1. Now when we add the third element, now the balance factor can be more than 1. So in this case we need to calculate the balance factor of all the nodes. So when we calculate the balance factor of all these nodes, we found that the balance factor of this node is making it imbalance. So and the balance factor of this node is -2. Now this is a RL balance. Now we can make a clockwise rotation, and after making a clockwise rotation it becomes a RR rotation. Again the balance factor of this node is still 2, so we need to make it balanced. So we need to make a rotation in such a way that its balance factor becomes either 0, 1 and -1. we can make a anti-clockwise rotation, and the balance factor of this will become 0. Now here we can see that the balance factor of all these nodes are 0, and now we again insert the last element 25, which doesn't change the balance factor of any node, and now the balance, this is a balanced tree because the balance factor of all the nodes are either 0, 1 or -1. So the right answer is 1 left and 1 right. Now I am handing it over to Pradeep, who will explain the code and the application of these AVL trees.
So now we are going to see the code for the AVL trees. Here is the code. So I have made a class, name is AVL node class. To create a node of this class, we need a node and the value of the node. And so here I am calling the value of the node as key. So self dot key, assigning key is assigned to the node, and self dot left, self dot right, and height. We are taking the default values for them. So here it is height is default is 1. uh, there here is a first function, get height. This function will create the height of the given node. If you give the node, it will return height if it exists, otherwise it will give 0 height. Next function is get balance. It will This function will calculate the balance factor. When you will give the root node, it will calculate the balance factor of that node by giving the difference of left subtree height and the right subtree height. Next function is right rotate. So right rotate function is when our tree is left skewed. At the time of left skewed tree, we will use this function. It will do some swapping between among the nodes. So here is firstly we will assign the left part of the node to the x, and after that we will swap a whole node and make the x as a root of the a new root of the tree. Let's move to the next page. Next page is left rotate function. Left rotate will do same work as right rotate, just in opposite direction. So we will make the root to y, and assign x to the left of the y. After that, our next function is insert function, which is the important function. Insert function is the main function. Here it will take a node and a value of the node. If node does not exist, then it will firstly create the node, and by calling the class. After that, if node already exists and key value is less than the node dot key, so we know in BST, if the value is child value is less than the parent, then it will be the left child, so it will assign to the left child. And similarly, the right child will be assigned in the else part. And after that, it will calculate the height, because when we will insert a new node, we have to calculate the height for all the nodes. So it will create node dot height for that node. And here is the main function to decide whether you will LL balancing will be needed, or another type of balancing will be needed. So if the balance is greater than 1, that means the left part was more skewed. So here it was the need of right rotation, so it will do the right rotation. In the next part, when balance is -1, so the tree is right skewed and it will do left rotation. Similarly, when there is a LR rotation needed, then balance factor will be greater than, and key value will be greater than left value, so it will be in the right side, so it will do LR rotation. And in the next part, it will do RL rotation. And finally, after calculation, it will return the node. Here are some applications of AVL trees. We use AVL trees in databases for fast data search, insertion, and deletion. We know their databases are very complex, so we use AVL trees so assign data to the nodes, and so that we can fastly insert, delete, or search. After that, it is also used in file systems, files, data organizations in our computer systems also, and version control systems. There is a network routing, and network routing, we know that there are very IP address to be created, so how to manage them, we use AVL trees also there. And these are the references from where I have taken the data for these slides, and all that knowledge I have provided to you. And thank you for listening me. Thank you.